Welcome back to The Explainer. You know, if you love dissecting how things work at a fundamental level, you are absolutely in the right place today. We're unpacking a massive, high-stakes engineering dilemma happening right now inside utility-scale battery energy storage systems, or BESS. We're talking about those giant, containerized sites that balance our power grids and store renewable energy. But inside these steel boxes, well, a silent battle is raging. It's a literal tug-of-war between keeping the system safely cooled and unintentionally draining away the exact power they were designed to store.
Okay, let's dive right into this, because this is the central question literally keeping engineering purists and system designers awake at night. Think about it. If you undercool a massive battery system, you risk catastrophic failure, total disaster. But if you overcool it just to be safe, you bleed energy constantly. So put yourself in the shoes of a system architect for a second. Where exactly do you draw that line? How in the world do you maintain a rock-solid safety margin without letting your cooling systems run away with all your stored energy?
Section 1. The hidden parasitic penalty, the threat inside the BESS container.
To understand why this is such a massive headache, we really have to look at the environment inside these systems, and we're talking massive scale here. Utility BESS assets operate in some of the harshest environments on Earth, right? From blistering deserts to freezing plains. So modern containers are intentionally packed to the brim with heavy, redundant cooling infrastructure. And look, the intention here is entirely good. Designers have to protect these multi-million-dollar assets against wild weather fluctuations and the intense heat generated by high C-rate cycling stress. But, and here's the catch, this noble quest for ultimate safety introduces a massive inefficiency. See, we're building these systems for the hottest hour of the hottest day of the decade, which means for the other 99% of the time, that infrastructure is way too big.
And that brings us to a really critical term, parasitic load. This is the internal energy consumed by the auxiliary systems. Think about your over-engineered HVAC systems, the pumps, the heavy-duty fans. They all require electricity to run, right? And where do they get that electricity? Directly from the battery itself. When you have excessive cooling capacity running during everyday partial load operations, it steadily erodes the asset's lifetime round-trip efficiency. It's honestly like leaving your car's air conditioning blasting on maximum freeze while you are just idling in your driveway on a beautiful, mild spring day. It is just an absolute drain on your fuel.
Let's move to Section 2 and see how this builds. The thermal safety tug-of-war, engineering purists versus asset optimization.
So, this tug-of-war essentially pits engineering purists who obviously prioritize absolute fail-safes against asset optimizers who are tasked with financial and operational efficiency. On the one hand, purists rightly argue that oversized chillers and heavy-duty liquid cooling loops guarantee temperature uniformity. And honestly, this is vital. It prevents accelerated cell degradation during those worst-case heat waves. You absolutely need your battery cells to survive a prolonged heat wave without catching fire or degrading prematurely. But then, on the flip side, asset optimizers point out that this excessive cooling constantly consumes power during normal partial load operations, meaning you are paying a massive continuous efficiency penalty for a worst-case scenario that almost never happens.
Which brings us to Section 3, stolen net export revenues, quantifying the drain. Now, that efficiency penalty isn't just some abstract engineering concept, it has very real financial consequences. We kind of have to start looking at this over-engineered HVAC system not just as a safety net, but as a silent thief living inside the battery container, quietly consuming incredibly valuable energy that was meant to be sold back to the grid. So the crucial point here is 8%. Now, I know 8% might sound like a minor single-digit annoyance, but in the world of utility-scale energy, it is a staggering number. An over-engineered HVAC system in a BESS container can consume up to 8% of the asset's total parasitic load.
To put that into perspective, every single sliver of that 8% represents power that was successfully generated, successfully stored in the battery, but then completely wasted on redundant cooling instead of being dispatched to the grid. And when you look at the 15 or 20-year lifespan of a utility-scale battery, well, that little slice compoundingly eats away at your financial returns. It adds up extremely fast.
And this brilliantly illustrates the core frustration in the industry right now. As the source material so bluntly puts it, every kilowatt dedicated to running redundant cooling fans and chillers is a kilowatt stolen from net export revenues. It really hits the nail on the head, driving home that motif of the HVAC system acting as a thief. Think about it. The power you are using to spin massive fans in 60-degree weather is power you simply cannot sell. It is quite literally revenue vanishing right into thin air. Moving on to Section 4, smart strategic design methodologies, resolving the engineering conflict.
Fortunately, the industry isn't just sitting still on this. We don't have to just throw our hands up and accept this compromise between safety and profitability. But the philosophy has to change. The engineering challenge is no longer about just throwing more hardware at potential thermal anomalies. We have to move away from designing systems based strictly on static, nameplate, worst-case scenarios. Actually, the old approach was essentially building a sledgehammer to swat a fly. It completely fails to account for the real-world, dynamic operating conditions the battery actually experiences day in and day out.
Now, what's really interesting about this is how we break down the specific, smart solutions that actually resolve this conflict. First up, deploying modular, variable speed architecture. This means your cooling fans and pumps can spin up or down depending on what's actually needed in that moment, rather than just being a dumb on or off switch. Second, scale precisely with actual cell heat rejection. Essentially, the system should only cool as much as the batteries are currently sweating, nothing more. Third, utilize localized fluid routing. This directs the cooling precisely to the hot spots in the battery racks, rather than trying to freeze the entire container uniformly. And by doing all this, point 4 becomes totally possible. You successfully balance those vital thermal safety margins with parasitic loss reduction. You get the safety without the massive drain.
So what does this all mean for us? Let's bring this tug-of-war directly back to you and the broader industry. As you look at the future of grid infrastructure, you really have to ask yourself, will your next energy storage asset be governed by static worst-case fears, constantly bleeding revenue to over-engineered fans, or will it be optimized by dynamic, variable speed intelligence that actually adapts to reality? The technology to resolve this conflict exists today. The real challenge now is changing the mindset of how we design for safety. Thanks for joining me for this explainer, and remember to keep questioning how things are built.